I'll grow up a bunch of them, one at 15, one at 20, one at 25, and I'll see which one grows the fastest at that temperature. Now I may put a plasmid in there, right, that has something that I want to express off that plasmid. And it has a resistance marker. So now I'll put in, let's say, amp resistant marker on it. And I'll put ampicillin into the media, which is kind of like a buffer. And then I'll grow that up. And then the ones that have the plasmid will or won't grow. But maybe they'll grow at a different temperature than the ones that would optimally, in terms of the rate that they grow and how much they grow, relative to not having that plasmid in it. So every time I make a change, I got to then recheck, but I already have a foundation for where I started with before I made that change, and I could just go a little bit up and a little bit down from that point. So I'm always going to do these tests to try to optimize it for both pH, temperature, time, and a variety of other things. So whatever you see on here that we do is something that's already known. When you guys move on and start doing research in a lab or whatever, you'll be doing something that's not known, so you'll take what's known and you'll start there as your foundation to start trying these different tests to determine what those conditions are before you start then assessing whatever it is you're assessing, transcription or whatever else, translation or who knows, whatever you're going to do. Does that make sense? So here we're just looking at how to figure out these things, how it's used and when and what's available to you to use will all depend on whatever it is that you're doing at that point. But very seldom does it cross over, just like business, right? I can't take the business model of one thing that was optimal in, say, 1970, maybe Walmart stores, right? Yeah, because they put this really good system in place where they had constant refilling of retail stores so that their stores always had a lot of stuff in it. Nowadays, you just do it online, so that model's no good anymore. It's good to learn the model, but then you have to make adjustments based on your system, right? And that kind of applies to everything, not just science. Go ahead.
I had a question again about the Henderson-Hasselbalch. So you have the pH equals pKa plus log A over HA, and then the other one says pH equals pKa over log base over acid. So you're always using pKa, you're not using pKb for the base of the acid?
They just renamed it.
Just making sure.
You can go POH equals pKb plus log acid over base. And of course, when I say acid over base, I'm referring to the conjugate acid-base, weak acid or weak base pairing. Right, just easier way. So I could do this and get the pOH. Remember I put this up earlier. There's your pKb. But I could also, if I have the pKb, can I figure out the pKa?
Yeah.
Yeah, how?
To the, yeah, 1.0
Using the Ka, I could then say the Kw divided by the Kb gives me the Ka. So I could always use this one anyways. Right? But if I didn't want to, I could use this. If I ultimately wanted the pH, then I'd just take 14 minus this to get the pH after. But these are equivalent, basically, in terms of you get the same answer however you solve the problem. You could try a problem both ways if you like. This isn't shown because I think a lot of people find it confusing. This was a question that was asked, I think, last week, or was it, what are we, a Thursday? Earlier this week, was it? Whenever you guys did that problem?
Oh, yeah.
Oh, that was last week because we did the exam on Tuesday, right? So, and I showed you this. So you could use the pKb if you wanted, if you had the Kb and didn't want to change it to Ka. But you could also change the Kb to Ka by just taking Kw and dividing it by the Kb.
Ratio will still be the same.
And then what the concentration of the acid base does matter which, top or bottom. So if you're using it for the pOH, acids on top, base on bottom. If you're using it for the pH, base on the top, acid on the bottom within the equation. But this changes pK, that's pKb, OH, H. Either way, it's okay. Okay, let's see where we at now. So it says, I have an example coming up here, and it says a buffer with a pH of 4.90 is desired. Okay. With the acidic acid acetate, so acidic acid is the weak acid, and its conjugate base is acetate, right? Make sure we're very familiar with those terms. Acid conjugate, weak acid conjugate base, that's the Brosted-Lowry definition and representation of acid-base pairs. Is this a suitable buffer system? It gives you the Ka of the acidic acid, and it gives you the pKa, or does it? Yeah, it gives you the pKa here, right? and it says this is relatively close. The pKa is 4.74. I want a pH of 4.9. See how they're not exact, but they're close, right? And then it has the ratio here, and it says, so now, is that a suitable system just based on that information, I guess is what it's asking.
Yeah.
Yes. pK. Now, what is the assumption there? Because there's no more information, so you can't plug in. And what else is involved here? Let me take this one off so this isn't confusing. Looking at this equation, what's relevant to determining this?
Oh, they're saying that the concentration is close to 1?
This, yeah. They're saying this part here they're not giving you.
Right.
Right.
And so that you're assuming that these are pretty close to each other and that this is pretty close to 0.
0, right?
As a whole. In other words, it's a very low number. So that the pKa is not going to change much relative to the pH. That's your assumption there, right? Because they don't give you any information on the concentration of your weak acid in your conjugate base. So just based on that, you could say, yeah, assuming this is fine, that's the assumption, then this is a decent buffer system because it has a pKa close to the pH. Thank you. Okay, does that make sense? Okay, so now let me get this back. We still have some time to, well, you know what, for someone who, he's an expert in this and it still took him a while, imagine how long it would take me. I probably would have spent all morning trying to do this.
It wasn't connected online?
I don't know. Yesterday there were power outages, so probably it's related to that.
It was like network issues though.
Yeah, I'll put this stuff here. Just on this.
We can stay till 1. It's gonna answer. You copied them, right? You copied them. Oh, yeah. The same thing. Was it more the back questions or the ones in the multiple choice? Hmm?
Okay, so from here on out, we're just going to focus on utilizing the Henderson-Hasselbalch to figure out pHs and pKas and stuff like that. Ultimately, that's all we're going to be doing from here on out, I think, throughout the rest of this. One of the things is that you could end up, we're going to get to the point where you have two different things, and then if you use a certain amount of one, then how much of the other do you need? And that's going to just be manipulating the Henderson-Hasselbalch equation, essentially. I think there are a couple small things that I need to point out. Okay. So here, so I think we've covered, what is all this? So here's the Henderson-Hasselbalch in your notes. Here's what we talked about. This is a problem we just did, I think, right?
We have, well, the example one?
This is the one I just talked about. So this is the one where we'll do next.
Sample number 2?
Sample number 2. Okay, so, and now maybe I'm going to try to move through these a little faster, now that you have a sense of this. Okay, so here we're asked to calculate the pH of a buffer containing 0.1 molar ammonia and 0.2 molar ammonium ion, and it gives the Kb. The very first thing, I want to make sure this is clear, because some of you missed this on the exam too. Why is the Kb given here and not the Ka? You can find the Ka, obviously, but why is the Kb given here?
Because you're getting the
Because this is
the
a
base.
basic solution.
Yeah, the NH3.
So I'm looking at a weak base and its conjugate acid.
Right.
Okay, And that was interesting because on the exam, some of you on that one question would put, you started with HF even though it told you you're starting with NaF. And of course, what your product is a big difference, right? You either have an acid as a product or you have a base as a product. If you start with NaF, you're pulling off the H from the H2O and you're left with OH minus, so that's a base. That's why you were given Kb. But then it asked you for K, it asked you for the pH, and some of you all kind of assumed you could just use that. Or inversely, right?
Gives you the Ka.
It gives you the Ka of the HF, but that's not what you used. So you used the NaF, that's what you started with. So then your product should have been a base, so you need Kb there.
Right.
In your K equilibrium,
yeah.
right? Okay. So here I want to make sure that's clear. I'm starting with NH3 and ammonium ion. I'm given the Kb for NH3, so I'm starting with NH3 plus water gives me NH4 plus OH minus, hence why I have Kb. Those things have to be settled in your mind as you go through these problems.
Right.
Right? For those of you that that was pretty easy. Now if I want the Ka, I'm looking at the Ka for the NH4 plus, I can simply take this Kw divided by Kb, and now I have the Ka, right? Okay, which is what you had to do on that problem on the exam, right? Okay. So now that I have the Ka, what else do I need to figure out the pH?
Your OH
Just use Henderson-Hasselbalch, right?
Right.
I convert this to pKa, so I take the negative log of that, right?
Yeah.
And I already have the base and the acid concentration. So it's what goes on top, base or acid?
The base.
The base, so I put 0.10 molar on top, 0.2 molar on the bottom. After I solve for the pKa, which is just this, 9.25, pH equals the 9.25 plus the log of the 0.1 over the 0.2. So there's my 9.25, there's this, base over the acid, and I solve. And that's my pH. I don't have to do anything else in terms of ice charts for this problem. There will be some that you do have to do it, but this one you don't anymore.
You could just find the POH and then find the pH.
Could have done that too.
Okay.
If I did that, what would change here?
The acid and the base would.
These would flip,
And then
and
you
this is going to be a different number, right? This is
Yeah.
going to be the negative log of this.
Right.
And then if I wanted then what would I solve for? I would have solved for the pOH here. How do I get the pH? 14 minus that. And you get the exact same number. Absolutely. And you could try that just to practice, just to see if, to make that clear. Okay, so this shouldn't be a problem. Buffer contains weak acid HA and its conjugate base A minus. The weak acid has a pK of 4.82. The buffer has a pH of 4.25. Which buffer component would you add to change the pH of the buffer to 4.72? In other words, I have a buffer that has this pH here, but I want the pH to be closer to the pKa. What different parts of this can I play with? Can I change the pKa?
No.
No. Okay, so I can't do anything. So once again, I'm looking at this. So I can't, I'm looking at this, I want this to go up a little bit, right? So this is already the way it is. I can't change that unless I use a different weak acid conjugate base. So what am I potentially changing here?
The base.
The ratio between the weak acid and the conjugate base. So if I want to increase the pH, what do I have to do over here is the question.
Add more conjugate base.
So you won't think I need to add more of this.
Right.
If I add more of this, what does that do to this area here? Makes it more,
It's greater.
Gives you a greater.
Yeah.
so I'm going to plug these in here.
Oh, you want to go down actually?
How, I want,
Yeah.
so the first thing I want to do is, why don't I just take this, I plug these in, I move this to this side,
Subtract that.
okay? And then I take the inverse log, and I see what that number is relative to this, to the ratio, okay? So if I take 4.25, subtract out 4.82, what do I have left? 0.7.
5.7.
57?
Yeah.
0.57, that equals the log of the acid, or the
Yeah.
conjugate base over the weak acid, right? Now I take the inverse, the anti-log, that's
0.27.
this 0.23 or 4?
27.
27, 0.27, okay, equals the A minus over the HA.
Mhm.
Okay. So this set here is 0.27. The question is do I want to increase this or increase this? By the way, see how I'm working this problem out? That's important. That's the same thing you should have done on the exam at times, is just work it out. So if I have 0.27 here equaling these two things here, I ultimately want what? But let me show you this too. This is important. This is 4.82. This whole term here is minus 0.57. So what do I want to do here? I want this number to what?
To increase?
Increase.
Right.
So what if this number was
To go to 0.
0.23? Then what happens here? Let me make sure this is clear. This is a ratio here, right?
Right.
So do I want this ratio to go up or down? Let's just look at it very
That
simply.
one you want to go
I want it to go up,
Yeah.
right? So let's say I make the ratio, I want it to be as close to 1 as possible, right?
Mhm.
So let's make this ratio at 0.8. 0.8, yeah, let's try 0.80 equal this ratio here.
Mhm.
So if that's the case, what did I increase? This one or this one?
The top.
I increased the
The
conjugate base.
Right.
Now if I put this back into this equation here,
Mhm.
what is the log of 0.8?
It's negative 0.1.
Negative 0.0, so the log of that, the log of 0.8 is negative
0.09.
0.09 or 0.1
Yeah.
or whatever.
Uh-huh.
Okay, so this plus this gives me what? 4.82 minus 0.09 is 4.7 what?
4.73.
73?
Yeah.
So I just made the pH go what? It went from 4.25 to 4.73. It went up.
And it's close to, yeah.
And it's close to the very close to the 4.72 that I wanted to change it to. So I didn't have to be that precise with it, right? Because the question only asked, what part of this ratio do I need to change to get it closer to that? And that change is I need to increase the conjugate base in this particular scenario. Because I need to increase this ratio in order to make the pH closer to what I wanted.
So this is how you get it more precise, but also just by looking at it, you could say, well, I want the pH to go up, so I'd want to add more of a base.
If you could see it that way. On a test, a lot of you got confused on some of those questions, right? Which is the same. So what am I showing you? You could just plug in numbers and see it yourself, right? So you don't have to actually just say, okay, I think it's this way. And then who came up to me and said I got confused and redid it? I did it the right way and then yeah. Because what's the first thing you start thinking of, wait, that's not right. Can't be right, right? Because you did it.
Okay.
You're not confident enough in your skills, even though you guys should be, right? And that's part of these classes, is to gain that confidence.
The step that you were at negative 0.57 equals log, and then you move the log over to get to 0.57.
This is anti-log, yeah.
Anti-log,
Yes.
to get to 0.57.
Yeah, you take 0.57 negative and second feature log, and that will give you the 0.27.
Or 10 raised to that.
So 10 to the 0.57?
Negative.
Negative
Yeah.
0.
You have to have the negative before.
So 10 to the negative 0. Oh, so you
If it was positive, you keep it positive.
You just put, usually it's second feature log, LOG. And that will give you the right, does that work? Yep. Good. Okay, so then that's what this is saying, that you have a lot more weak acid than conjugate base, and therefore you need to increase the conjugate acid, I think is what they're trying to say here, yeah. So you just add it, and we were able to figure it out just this way, without it. So however you want to think about it, just make sure you think about it properly. If you're not sure, plug them in and evaluate it that way. In fact, doing this is important because later on, if I was solving for this one, I would just move this over here. and then I could solve for this. Or if I was solving for this one, I'd move this over and this down. If I knew one or the other, I could now solve for the other, which we're going to do, I think, at the end of this part of the chapter.
It's saying that the acid would be more than the conjugate base, right? What's that?
You have 0.27 is the ratio here. That means you have more of this than this. If you had more of this, it would be above 1, right? So it's saying that you need to increase this in order to get it closer to the pH.
Wouldn't the arrow need to be the other way then?
What arrow?
Wouldn't it be less than?
What arrow?
The first part.
The concentration?
No, for-
This is greater than this.
Yeah, that's what it's telling you right now.
0.27 means that this is greater than this. This means that this is greater than this.
That's what it is
That's
right
why
now.
it's 0.27. If it was 1.27, this would be greater than that.
Oh, okay. So that's not trying to show that,
What is it gonna do?
that you need to add more of the.
This is telling you what you have here currently.
Oh, okay. Not what you need to add more.
Then, as a result of this, to correct it, to get to that higher pH, then you must add more of this. And that means you're taking it from 0.27. In our case, it worked out at 0.8, right? Is that how? I think we did 0.8 or 0.7 or whatever. Is that okay, Peter?
How did you get to the 0.8? Did you just?
I just
Pick that arbitrarily?
I just increased 0.27 to something.
You can even. put
I looked
one.
at it and said, well, I want to move up about, I'm trying to move up from this to that about 5.5. So I estimated 0.8. I could have estimated 0.7. I could have estimated 0.9. Either way, the point being is, for this question, is that this needed to go up because this needed to go up in order to get to a higher pH, which is what we're trying to accomplish. I just arbitrarily picked a number that worked.
So had they given you the numbers, you could put like test numbers to see.
Yeah, that's what I did.
I mean, like, had they given you concentrations of HA?
Oh, and the concentration, I mean, if you knew the concentration of one, you could solve for the concentration of the other, right? That was what I showed here. In this case, it's not asking, we're gonna get to that. We're gonna see with concentrations in a minute. This is just looking at the ratio.
The ratio, yeah.
That's essentially how you would solve a problem like this, is just plug in your numbers.
Depends on what the problem's asking. If it's asking this specifically, I think the problem with your question is, and I could be way off here, but based on how you're asking it, I kind of get the feeling that you're asking it as though this is a Henderson-Hasselbalch type of question. And this is just one type of a Henderson-Hasselbalch question, not the traditional Henderson-Hasselbalch question. This is, right, so in other words, I could ask a lot of different things that require the Henderson-Hasselbalch equation.
Yeah. like
This
I
is,
just-
it's this specific type of question where you need to use the Henderson-Hasselbalch. Yes, this is how you solve it. But I'm gonna ask you multiple questions that have nothing to do with this, that give you other information, and you have to use the Henderson-Hasselbalch to solve it.
Right,
Right,
yeah,
okay,
I
so-
just wanted to make sure that I understand how to figure out which one's higher, and I guess.
Yeah, in this context, yes. But this isn't the only context you're gonna see. That's what I wanna make sure is clear.
Yeah.
Right, okay. That's important.
Just to build your understanding.
Yeah,
Understanding.
yes. And that's exactly what happens sometimes on an exam, right? Where you're expecting, well, this is the only way I use this. And then when I ask a slight different thing, all of a sudden it's, well, wait, what do I do? And that's what I don't want you to fall into with that question, right? Okay. Okay, so now let's take a look. Now, this is just solving for the pH of a system. Now what if I already have the buffer system and then I add an acid or base to it? I will now want to see the fluctuation of the buffer system. How does that change the pH now? Or pOH potentially, but I think this book always focuses on the pH angle of it. So here I'm going to add an acid or a base to the buffer system, and then I'm going to look at that change in pH, which presumably would be very slight, because that's the whole point of having the buffer system, right? Okay. So the first thing I need to do is I need to look at the stoichiometric calculation. In other words, the ratio in the balanced chemical equation, remember, always put the equation up first. I need to see how much I start of the acid and how much of the conjugates, and then how much is used up as a result of that, based on the stoichiometric ratios. And then from there, then I can do the pH calculation, which essentially this is just the Henderson-Hasselbalch, right? Okay, so that's all. This is not that significant of a slide, other than when I add the acid or base, I now need to do the stoichiometry to determine how much is gained or lost, right? Because then whatever is left, that's what I'm now assessing as the new pH. Okay, and then once again, to do that, I just do the Henderson-Hasselbalch. So let's just work. I have 1 liter, which is really convenient. Take note of that, because if it's not 1 liter, then I need to make a lot of adjustments. I also should state, when I go back here, when I'm looking at these relative amounts, what am I looking at there? What type of unit? Let me rephrase it to simplify it. What am I looking at?
Millimoles?
I'm looking at moles.
Moles, right.
Whether milli or some prefix associated with it definitely can do that. But I'm looking at the molar ratio, right? Because in a balanced chemical equation, those are moles.
Right.
So I'm going to use the ice chart in order to determine the stoichiometric changes of each thing. And then, once I have that, when I use the Henderson-Hasselbalch, how do I have to change that?
Oh, the initial.
Molarity.
Right. Uh-huh.
So I need to divide by the volume. Really important, which is why the first thing I said when I changed this slide, how convenient is 1 liter. So I don't want you to get the impression that we're going to solve for the moles, and then the moles are what you're putting into the Henderson-Hasselbalch. You're putting in the molarity. Since it's 1 liter, it's going to look the same, right? Hence why I wanted to catch that right away. I was like, that's why I said that's convenient. Okay. So I have a 1 liter solution that has 0.1 mole of acetic acid. That's my weak acid. Here's the Ka of that. And then I have 0.1 mole of its conjugate base. Nice, 0.1, 0.1. That's pretty good, right? And since the whole thing's 1 liter, that means I'm going to have 0.1 over 0.1, at least initially. And then let's calculate the pH of just this system. Okay, so before I add the sodium hydroxide, then I'm going to add this as this is a strong base, and that's going to move one of these one way versus another, and then I'm going to reevaluate the pH. So before I add the NaOH, let's take a look. I simply take the Ka, I get the pKa, right? And then I put 0.1 divided by 1 is still 0.1, but I want to make that clear. And 0.1 divided by, so this whole thing is going to be what?
1, 0.
Yes. 0.1 over 0.1, that just means, in the pKa here, if I take the negative log of this, I get 4.74, so the pH is 4.74.
Right.
Okay, no big, this is before I add the sodium hydroxide. That's the easy part, right? That's just what the buffer's pH is. And it's a good one because these are real close to each other, as said, and ideally we probably want a pH around that amount, 4.74. Now I'm going to add sodium hydroxide, and I'm adding 0.01 mole of sodium hydroxide. First you need to know, sodium hydroxide, does that separate completely?
No.
Okay,
Yeah,
good.
yeah.
Yes.
Okay.
So then 0.01 mole of sodium hydroxide, how much hydroxide am I getting out of this? 0.01. Okay. So 0.01. So now what's the equation when I put this into the buffer? What's happening? What's the equation I'm using?
Adding that into the acid.
So I'm adding the OH, that's the important part here, right? So I'm saying OH, and it's going to bind to either the acid, the weak acid, or its conjugate base. It's going to bind to its
Weak acid.
weak acid. So that's the HA. In this case, that's HC2H3O2, right? Then it's going to go where? H2O plus
The acetate.
the acetate, C2H3O2 minus.
Mhm.
Okay. Everybody agree? How much of this am I starting with?
Oh, 0.01.
0.01 mole, right?
Mm-hmm.
How much of this? 0.1 mole?
0.1.
And this? Nothing, and this?
Nothing. 0.1.
0.1 mole,
Yeah.
okay? And now, all of this goes this way.
So that's negative.
So this then becomes minus 0.01 mole, right?
Uh-huh, that
And
gives
its
zero.
overall is going to be 0 as expected. That's
Right.
the change, and this is the ending, or when the whole thing goes into equilibrium.
Mhm.
This now, how much? This is what's the ratio here?
Also 1 to 1.
1 to 1. That's important, right? If it was a 2 to 1, I'd have to account for that.
Multiply.
So what's going to happen here?
So subtract also.
So this is going to subtract 0.001,
Mhm.
and this is going to what?
Add.
That's going to gain 0.01 over here, right?
Right.
So then over here I'm going to add, I'm going to have what, 0.09?
0.09, yeah.
And over here I'm going to have 1.1.
0, 1.
Or zero, yeah, that's right. Zero, that's zero, right? 0.11.
Yeah.
Right? Everybody see that? Did the ratio change? It went from
Oh,
Yeah.
this
on top of the bottom, yes.
Oh,
to this.
Yeah.
yes.
Is that going to change the pH?
Mhm.
A little bit, yeah. And that's the whole point. That's how the buffer system worked. Dieter?
Why is the acid the same as the conjugate base initially?
Why is what?
The acid there and then the conjugate base is the same initially.
Oh, that's what it was given.
That's what they do.
0.1 mole acid, 0.1 mole base. 0.1, 0.1.
What we
Okay.
started.
They
that
give
what
it
you
to
mean?
us.
Yeah.
Okay. So then, okay, so this is that stoichiometric thing that they were saying before. So let's, okay, here we go. So this is this wrong. This should just be acetate here. So when you're looking at the buffer system and you're designing the equation, and that's why I wanted to do it here to see, you take whether you have an acid or base, and then that's the thing that's now reacting. So that's your equation. That's why it's not invert. It's this direction. Because what I'm trying to do here is I'm trying to solve for the change in amounts of each thing as a result of adding that base or that acid. And then I simply plug those numbers into the Henderson-Hasselbalch. And that's going to change the pH because you're changing the ratio of the acid and the base.
On the last chapter, we learned about the mixture of acids. Is this using the same chain or thought process as to using the strong acid equation, or the strong mixture equation versus the weak? Because you could have used H2 into water and gives you the hydroxide, and then from this strong you can add that into that equilibrium ice chart, which is what we have been doing before. This one is going the other way around. It's using this.
Not sure what you mean. Huh?
That's an acid base neutralization reaction, no?
Right, that's a strong base.
This is a strong base, yes. That's
Right.
why it all is used up.
But before we have actually learned that we add in the strong base molarity into the weak acid strong base conjugate base ice chart. I'll ask that later.
Yeah, I'm not 100%. I'm not quite sure what you mean by that.
Right. Okay.
So you know what, for example, just when you're writing the equation out, you know to put the OH first,
But-
because I get what
You
you're
could.
saying.
The only reason, okay, so how this equation came out, I already know I'm putting the base in. The reason if I was putting an acid in, I'd put H plus in. I'm putting the base in, I'm putting this in. Because then that tells me what part is going to attach to the buffer system. Because I have both of these things, so how do I know which one of these to use with this? And so I put this first just because now it makes it easy to say, oh, this is a base, I need the acid part of the buffer system on this side, and that's going to create more of the conjugate base on this side. Is that what you mean?
Yeah, but then also, how would you recognize that you're supposed to put the acid first and the conjugate base on the base?
Because you're putting this in.
This,
Hold on. So if I put this, why would I mix it with this, I guess is what I'm asking.
oh yeah, no, that would not have a
Oh, so you
reaction.
have to, that just.
What's it going to do?
Two bases, yeah.
It's not going to do anything.
Right.
Is that okay?
Yeah,
That
I-
help?
I
Okay,
didn't-
good,
I
good, good,
didn't-
good.
I can't
Yeah, I wasn't clear on, because I'm thinking that's automatic, but now I see what you're
I can't
asking.
see the other side's equation, so.
Okay, right? What was it? I saw. Does that help? Okay, so while you're leaving, just real quick, so now that I have this adjustment, all I do is now plug the new numbers into the Henderson-Hasselbalch. This is now 0.11 and this is now 0.09, and you can see now what my new pH is at 4.83. It went up because I put in the base, but you see it only went up a little bit. Okay, and with that being said, we'll finish this off next week. Have a good weekend. I can't hold you back anymore.
Doctor.